In this unit, we look at an extension of the work we've been doing with integration to a new field of study that arguably is more important than integration itself. And this is the area of differential equations. If you look at any calendar, you'll see differential equations as one of the main continuations of calculus. You'll see second-year differential equation courses, you'll see fourth-year partial differential equation courses. This is really a rich area for scientific and economic modeling. Anyway, this is an important topic that we're introducing here in Math 121. And what we're seeing here is really the tip of the iceberg in terms of studying differential equations. But I just want to make it clear that this is an important topic that returns and can be studied or applied in a wide range of topics. And we'll see a bit of that as we go forward to get some glimmer of the connections between the calculus ideas of differential equations and in particular the applications of them in various fields. Let's start off with what a differential equation might look like. So key word here, equation. So if we have an equation here, something with an equal sign, that's all we're talking about. The only thing that makes it a differential equation instead of a regular equation is that somehow there's a derivative involved in the equation itself. And the reason we look at these is because many of the laws of nature, of economics, are very easily expressed in this form. Let me show you how that works. One way to define the exponential function turns out to be this equation here. The derivative of y with respect to time is equal to y itself. Well, what that's saying is y is a function equal to its own derivative. We could get more graphical about it and say the slope lines or the slope of the tangent lines are equal to the y-coordinate, things like that too. But I think in terms of algebra, it's easiest to say it this way. Y is a function which is equal to its own derivative, or when we differentiate, or which when we differentiate it, so when we differentiate it, we get the same function back again. And that, expressing it that way, I think makes it very clear that's the exponential, the natural exponential we're talking about. All right. So that's an equation with a derivative in it. So this is a differential equation, and somehow we're talking about the exponential function here. Well, this would be a solution. And how does that terminology work? We'll explain the idea of solutions as we go through this. We're going to take a few weeks on differential equations just to expose you to the ideas over time, because there's a lot of, it just takes some practice getting used to this new area. All right, so what we'd say is y equals e to the t is a solution to this dE. All right. Now, one question we might ask is, you might not ask it right away, but it's a question that's going to be important moving forward. Can we modify the solution we just found and still satisfy this equation? In other words, is this the only solution? Well, my answer is going to be no. That's why we're going down this road. But it might not be obvious how to generalize this. Some people would suggest, what if we generalize this? Let's make it not a k. Let's make it e to the ct. Let's make it a, e to the at. What if we had a different exponential and asked, is that also a solution? Well, let's check. And here is an important idea for differential equations. Checking a solution is just as easy as plugging it into the left-hand side and the right-hand side. So we take our solution here and put it in the left-hand side, which would be the derivative of y And we said, here's our proposed solution, e to the at. And if we differentiate that, we'll end up with a e to the at. Meanwhile, the right-hand side, which is just y, is e to the at. So what we've done here is we've just plugged the solution, the proposed solution, into both sides. Into both sides of the equation, and see if we get the same thing on both sides. All right. And wait a minute, as soon as we look at that, there's our left-hand side solution, there's our right-hand side of the equation. These are not equal to each other. So when we plug this solution into the equation, it doesn't work. Both the left and right-hand side are not equal to each other. So that tells us y equals e to the at is not a solution. Okay, well, what other alternatives could we think about that generalize y equals e to the t that don't involve changing the rate of growth or decay here? Well, let's make another guess. Guess number 2. And it's worth thinking about this yourself before I write down my guess. How else could we generalize this? Well, let's take a look at the form of the equation. Certainly we want something exponentially, because we know something exponential with e to the t, because that's what makes something the same after we differentiate it. We see if we put any multiplier inside the exponential, then we get that constant out, so we get something different. So how could we change their solution to still satisfy this? Well, I think, just imagine multiplying both sides by a constant. Let's do that. Let's add this constant in front of our solution and then check it. Well, the left-hand side is the derivative of y, and this time we said the derivative of c e to the t then, which is just c e to the t. That's sounding pretty good, because the right-hand side is just c e to the t, and now we have two things that are equal, which tells us that y equals c e to the t is a solution, and even more importantly, for any value of c, we will have a solution. So this would be a general, what we call a general solution, not just the exponential, but a constant times the exponential will satisfy that equation. All right, think about that for a bit. We'll move forward and see where we can get. All right. Now the natural e to the t function doesn't occur in nature very commonly, very frequently, or just as is. What more typically happens is that we change the rate of decay or the rate of growth. So let's take a look at the slight modification to the differential equation and ask, or the goal here is really to find a function y which, when we differentiate, equals itself times a constant, equals itself times k. And k would be a constant times. Well, in fact, we already saw this just a second ago. We would say it's e to the kt. That would be our guess as to the solution. And we know that when we differentiate that, we're going to get a k out front. So when we differentiate, we're going to get a k. There's a k in our equation on the right-hand side. And let's make it even more general. So the C here, it made sense in the last example. Hopefully it makes sense in this example as well. Let's just make sure that works out the way we expect, and there's no reason to expect it wouldn't. Check the left-hand side is the derivative of y, or the derivative with respect to time of c e to the kt, and that would be c times k e to the kt. Meanwhile, the right-hand side is simply k times y. Well, that's k times c e to the kt, because there's our y. Let's bring this down here. There's our y. There's our y. And, of course, that's the same rewritten as c k e to the kt. So these two expressions here are equal. And if those two expressions are equal, then we have found a solution. We've found a y that satisfies the equation. And let me express this in a different way as well. It's a family of solutions. And why is it a family? Well, they all look basically the same, except we get to choose the value of c that's out front there. We get to choose the c value. So there's actually multiple solutions, and we can pick one that satisfies some other requirement if we like. All right. Expressing this in English, here's this dy dt equals k times y. What is that saying? Well, it's saying the rate at which y changes, dy dt, is proportional to, and remember the phrases for this, is a constant times y itself. And how does this play a role when we're talking about physics examples or chemistry or other models? Well, if we have proportional to but with with positive, that's one way of saying exponential growth. My rate of change is proportional to the amount I have now. Oh, if I've got a bank balance of 10,000, I'm growing at a rate proportional to that 10,000. If I had $100 million, my rate of growth would still be proportional to the amount of money I have. So you'd have an interest rate in here. When you have something like decay, like radioactive decay, the rate at which you lose radioactive material depends on how much you have. The more you have, the more quickly you lose things, because you're losing things as a percentage of your current amount. And so this differential equation is capable of capturing those ideas in a very compact form and leading us to the solutions, the exponential growth and exponential decay, that we know describe these kinds of applications or these kinds of models. We're going to explore that even more thoroughly as we move through the unit.